Welcome to the course on two-dimensional signal processing, principles and practices. As we are doing the signal processing overview, especially the fundamentals of 1D signals, we'll continue to do the classification of the signals and the operations on these signals, either continuous time or discrete in time. As we have seen in the last lecture, this signal operations can be of two at the maximum. That is, here is time shifting and scaling. So for a given signal x of t, if you want to shift that signal and scale also, or the two operations which we had seen separately in the previous lectures can be combined together to perform, suppose x of t should be done with x of a t minus b. So a t, the t is here multiplied with a and delayed by b here by t minus b. So this a and b are constants. We can choose whatever the way in which this a needs to be decided. So how do we combine these two operations in one signal? That is, what is the way in which we should do it? So the order of operations, if you want an x of a t minus b, then first thing preferred is that x of t should be delayed by b time units. That is, the delay, the time shifting operation is preferred to do it first, and then in this case perform the time shifting delay by b, the b units. That can be the any value 2.356, any of the real number here, and then do the scaling operation. So perform the scaling operation on the time shifted signal. It is t minus b, and then either compression or dilation can be done on that delayed sequence, that is by a. So the second operation should be the compression or the expansion. So for example, or we can also do the second way, that is the preferable way which I had shown you. First delay it and then scale, shift it and then scaling, and to perform the same operation, x of a t minus b, that's equal to x of a t minus b by a. So if we see the operation, the order of operations, how do we do this? First, making this time scaling in this operation. This is the second way of getting the same x of a t minus b. This perform time scaling, that is compression or expansion by a. First do this t a t, that is x of a t here, and then perform the shifting. The shifting, when we do, we should be very careful because it is already compressed or dilated, the x of a t. So the delay should involve this a as well. So it's not simply shifting it by b, it should also shift by b by a. The shifting should be the b by a. So first, if we prefer to do scaling, then the dilation in the, or compression in this case, if x of a t, then perform the time shifting by b by a. Okay. So these are the two ways in which x of a t minus b can be obtained. So these two are combining the time shifting as well as scaling operation. Either first do the shifting and then scaling, that's preferable way, or we should be careful when we do the scaling first and then shifting here. So we take an example. So the right side one, which shows that t, the time varying, and the same example we took, this is x of t. The time is the independent variable, x of t is the amplitude here, which is shown for a continuous time signal. And when we want to do, suppose x of 2t minus 2. Okay, so in this case t minus 2, so first we want to do the shifting, then t minus 2 has to be performed here. After performing t minus 2, that is delay by right shift t minus 2, after getting x of t minus 2, and then do the a part, which is 2 here, either the compression or the dilation part here. So x of 2t minus 2 on the t minus 2 signal, what we have obtained. So when we do this, when we delay it t minus 2, this would be starting here by 5. When we try to multiply it by 2, the t minus 2 by 2, so that would compress, because the signal t minus 2, x of t minus 2 would be starting, this would be delayed, and this point would be here, that is 13 would be delayed to 15. So in that case, after performing the delay, if we try to multiply by 2 the time base, so it would be not at 5, that is t minus 2. After that, we do the multiplication by 2, in which that 5 is shifted to 2.5, that's 2.5 to 7.5. The signal which is now compressed because of this multiplication to 2t minus 2. So the multiplication A is greater than 1. So the output which we get is the compressed signal. At the same time, it was delayed by 2 time units as well. So this is the combined operation of the x of t, that is x of 2t minus 2. If we take the same thing, this operation in the discrete also, the discrete signal x of n, where time shifting and scaling needs to be combined. So for that, similar to the argument is also hold for discrete. So x of a n minus b. So order of reference, first delay this n x of n by b, that is the delay whatever was given for that particular signal b, and then do the scaling, which is compression or dilation, that is a here. That is the second part of this is combined operations. Or we can, similar to the continuous time signal, we can change the order as well, but we need to, when we do the second step, we should be careful in the delay thing. They perform the time scaling, that is a x of a n, obtain it as the first step. This is alternative way, and this perform the time shifting or the delay by b by a, that not only b, it should, because it is scaled already, the n is scaled already, so you need to delay it by b by a. So the same, the example which we took in the last lecture, that xn. So this xn, when we try to do 2n minus 2, similar to the case of the continuous one. So the minus 2, you delay it, so it would, this 4 would shift to 6. Okay, so the 12 would 6 to 14. So that is x of n minus 2. So after performing x of n minus 2 and then multiply this whole base n minus 2 by 2, that would compress the signal. So in that case, if we were, where it was 6, it has now moved to 3, that is compressed, and then where it was 12 to 14, that changed, it is now at 7. So that is a compressed sequence, because a is greater than 1 here. So if a is less than 1, it would be dilated. So here it is compressed signal. So this is the outcome of for the x of 2n minus 2. Now shifting and scaling to the precedence for the time sequences, what is the rule? I said first shift it and then scale it. That is the operation of the combined time operations here in the, for the continuous as well as discrete sequences. Now the case of system properties, we have seen some of the signals and the classification, and we would also deal with the systems, because we will be processing the signals. So for processing the signals, either 1D or 2D, we need systems. So the systems are as the block diagram this shows here, the system which has x of 1, x of 2 and x of n are inputs, and the system outputs are y1, y2, yn, up to yn. So it is shown that there are multiple inputs and multiple outputs, n inputs and n outputs here. This input can be one input and one output. In that case, that system would be single input and single output, or likewise it is shown here multi input or multi output also possible, and the other way around. So the input can be one and output can be multiple. So in that case, single input, multiple output, or in that case that multiple inputs can be given and only one output is maybe necessary. In that case, multiple input and single output system. So these are 4 categories of the system according to the input output nature of the system defined. This can be CISO and MIMO, and all the 4 categories can be obtained. Whereas what is the system now? The system, which is actually the collection of components. This can be a hardware element and it can be a software, or it would have some components which is assigned to do some task. So this task will be given through the input, and it can be, suppose considering the signal processing system, in which that if the signal is given, whether this system is going to just to amplify the signal, or it going to filter some of the frequencies from it and retain some of the frequencies. So this can be thought of as a system. So it is a collection of components where the system would act on the input for the signal processing systems. So as I said, this would process the signal which is given as an input, and the response what we get is the output. The system responding to this input is the y of t, or y1, y2, the multiple inputs. So as we have classified a CISO, single input single output system, or single input multiple output system, or the multiple inputs and single output system, also multiple input and multiple output systems. So this is a very basic idea of the system. So we'll further explore this based on the systems, what are the classifications and what is the mathematical model of these systems and so on. So the system, if we take the examples, for example, the RLC, RL networks, as in the filter designs you use it, RC networks, and then RLCs, RL networks and the electrical systems, and also mechanical system, basic mass spring damper system, that's also an example. The translation systems and rotational systems are the few examples of the mechanical system. The electromechanical systems also can be considered as this one, and armature control DC motor, field control DC motor. So these can be mathematically modeled even. So these systems example, and liquid level system, for example. And we have this filters, different filters and analog digital systems, all of them, they can be combined. So these are the a few examples of the systems. And now come to the classification of the system. So we can classify these systems based on some of the properties. So the first category is that linear and non-linear systems. So the system can be linear or non-linear, or it can be constant parameter and time varying parameter systems. So system would have certain parameters, that parameters are varying with respect to time or it is constant. So based on that, the systems can be classified as constant parameter and time varying parameter systems. Also the system can be whether it needs the inputs of the previous instant or time, not only depending on the present time, is it depending on the previous instant of time, x of n minus 1, or x of t minus 1, some instant before. Then you need to store that previous instant values of the input as well. So in that case, this system need a storage. So that is memory system, that is called the dynamic systems. Okay, so the instantaneous systems are responding only to the present input x of n, and the y of n can be obtained. So there is no memory needed in this case. That is, you need not store the past values of the input in case of instantaneous system. So that can be instantaneous and dynamic systems, other classification. And then causal and non-causal systems, we'll see with the examples also, causal and what are the non-causal system. These are the fourth one. And the continuous time and discrete time systems, as we have classified the signals as continuous time and discrete time, similarly systems can also be classified into continuous time and discrete time systems, wherein the continuous time, the every time instant it is valid, and then the discrete time, the time is only valid for certain instant of time. That is analog and digital systems, also it takes completely the analog inputs and gives the analog output. Digital systems take the digital inputs and then the digital outputs responding to it. Or some of the systems are invertible and non-invertible systems as well. In this case, whether the system can get its inverse or not. So we would see with examples that invert and non-invertible systems as well. Finally, we can also classify the system to be stable or unstable. So we want the system to be stable in case of processing. For processing the signals, it needs to be stable. So we will see what is the difference between the stable and unstable systems. So first we will take the linear system as the top priority to the classification. So what is the concept of linearity? As we know that it should have the superposition, it should obey the superposition property or the additive property, and the second one is the homogeneity or scaling property. So both of them needs to be satisfied by the system. So then the system will be linear. So if for example the superposition, how do we say that this is obeying the superposition theorem? Here, if the input is x1, the system input is x1 and it yields the output as y1, and the different input x2 we give, and that system would give the output y2. This should be true for all x1 and x2 values, that is this should give y1 and y2 only. If this individual input x1 is yielding y1, individual input x2 and it is giving y2, and if both are combined, x1 and x2 are combined, that is added, and the output should be the y1 plus y2, which was obtained for individual inputs. So individual x1 has given y1, x2 has given y2. When you combine these two, they should give the y1 plus y2 output. So then the superposition property, the theorem is satisfied. What is the second one? The scaling or the homogeneity property. If you give an input to a system X and it would give the output as Y, then for all real or imaginary value of K, this should be noted here, that when X is given with K or multiplied by K. Okay, so this K need not be a real number, as we did in the time shifting operation or the scaling operation, like the combined operators and all. The K need not be real. Actually, K can be even imaginary. So if K is imaginary, then the output should be multiplied by K. So if you multiply by 1, it should multiply by 1. So if you 1 plus j, then the output also should be 1 plus j. So the imaginary K is also should be valid in the case of scaling or homogeneity. This should be valid for all K1 and K2 constants, any K value of this K1, K2, anything. So combining these two properties, superposition theorem and the homogeneity. So K1 X1, that is scaling, K2 X2, and if you add these two inputs with the scaled value K1 and K2, output should be K1 Y1 and K2 Y2. So then the system is linear. Okay, so for this should be valid for all X1 and X2 inputs which we are considering here. It should be valid for all the X1 and X2. So then now linearity is that if it is not satisfying the case of superposition and homogeneity, then the system becomes nonlinear. That is going to be nonlinear system. And what is the response of the linear system? So linear system response needs to be noticed, that how we can have this, what are the components involved in that response of the linear system. For example, this single input and single output system. So this same thing can be extended to multi input, multi output, or multiple inputs, multiple output systems as well. So the system output is going to be the response of a linear system. It should going to be t greater than or equal to 0. It would be due to two independent causes, that is two different things. It involves two different things. What are those things? Like, that is a zero input response, that is the response of the linear system would contain the zero input response. That means zero input, the name itself implies that zero input is 0. That means the system input is 0. The input is absent for the system. In that case, the system is acting on something, that is the initial conditions. So it is due to initial conditions at t equal to 0 with x of t equal to 0. The x of t is the input of the system, and for t greater than or equal to 0. So at t equal to 0, the system has only the initial conditions. It does not have any input, or no input is applied to it. So in that case, what should be the response of the linear system? So that's the zero input response. Okay, and then the linear system has another response, that is the second independent cause. As we are discussing two independent causes. The first one is this zero input response, and the second one is the zero state response, in which that zero state, meaning it implies that all initial conditions are 0, and this is only the input which is applied to it. The system is responding to input what is applied to it when all the initial conditions are 0. So that is only for the input x of t for t greater than or equal to 0. So these are the two independent causes. So the system, so the total response would have two components: zero input response and zero state response. So zero input response is due to only the initial conditions, and zero state response is only due to the input what is applied. So this about the response of the linear system. Now we take the time invariant and time varying property. So linearity can be tested, and what are the response of that linear system has been found. Now the thing is, what is time invariant, or what is the time varying systems? Okay, so how the property is defined here. What is the property? Suppose we have the system. The system operator is h. It is doing something on the h is the operator, is performing the task what is given, and h on x of t acting on it, giving a output y of t. Okay, so this is a continuous time system. X of t input, h is acting on x of t and giving an output y of t. And then what we do is delay this y of t as the right shifting, like right shifting, delay it for time units, some time units, t seconds. Then the output would be just t minus t. Y of t is t minus t. So this y of t, when you delay it simply, that would be that is the output y of t minus t here. So now if we take the other category here, so x of t, that means you have the input and delay the input for some time units, xt minus t, and pass it through the system, that is h operating on this input instead of this input. Okay. So h x of t minus t, then it would give y of t minus t. So both the inputs must be same, whether the input is straight away given to the system and then delayed it, you would get a certain output, or you give a input x which is delayed and then given to the system, and you would get an output. So these two outputs should match, then the system is time invariant. That is irrespective of the time delay, whether it is applied over here or it is applied over here, the output would be same. For example, if you are taking a reading today with your device now and getting some output, and then you take this same reading next day with some time delay on the same system, then the output should be same. So then it would be the time invariant system. If these two are not same, then it is time varying system. The system would be time varying here. So taking the x of t, this is signal, and it is when you give it to h, that is the system, this input, and it would give an output y of t. Okay. Now if we delay it and give it to the same system, delayed input would produce y of t minus t. Okay. So this y of t, x of t, passing through y of t and then delay it and come over here, or first delay this signal, delay it and then give it to the system and come over here. So both should be matching, either you pass through this or this way. So the y of t should be, the output should be y of t minus t for the case of time invariant systems. Now coming to the instantaneous and dynamic systems, as I told, the system output is the instant t depends only on the present input, not any past or future inputs, so that you need not store those values. Okay. So storing needs some memory, so that is called the memoryless system. And if the output, system output, is determined by the past t seconds, that is it is depending on previous inputs, then the system is going to be the memory system or dynamic systems. It will have finite, it may need that finite memory, in this case dynamic systems. Now we will come to the causal and the non-causal systems, where the causal system is physical or it is also non-anticipative systems. How? That is, if system output at some instant t naught, suppose you want the response of the system at t naught, to decide based on what are the inputs required for it. Y of t is going to be x of t or x of t minus 1 or x of t minus 2. So any instant of time, it only on the value of input x of t, which is t less than or equal to t naught. Okay, so that means it can depend on past values of inputs only. It should not expect the future inputs to decide on the present output. Okay, so those systems are called the causal systems. So only past and present values of inputs, not on future values of inputs. So if it seeks for the future, that is anticipative. So this was non-anticipative, and physical, it is realizable. It is because at present instant I am just expecting only to depend on the past or the present input. So that is, those systems are called the causal systems. And these causal systems, if we take as a system, the output cannot start before the input is applied. Of course, that input should be applied so that the output will be available. So the non-causal systems are anticipative. The system knows the input in the future and acts on this knowledge before the input is applied. It is depending on the future inputs. So if y of t is depending on x of t plus 1, That means then it is depending on the future input, it is not on the present or the past inputs. So those are non-causal systems. So these are, suppose for example, y of t equal to x of t minus 2, that's okay. If t minus 2 is possible, that is going to be a causal system, but adding this x of t plus 2. So if suppose at t equal to 0, I want y of 0 equal to x of minus 2, that's fine at that, and x of plus x of 2. So this input is not known at this point. So this is expecting the future input x of 2. So this is a non-causal system. So this system has no practical purpose here. So because future input I cannot wait for till now this. So coming to the some of the examples of these systems, like the discrete time system, where is y of n, we take this h is the system operator acting on x of n, h is acting on x of n. So what is the y of n here? So likewise we can take some of the systems. So how we can define, for example, the moving average system, which is very common to use the find the signal average. Okay, so the y of n equal to, the system obeys this equation 1 by m, where summation k is varying from 0 to m minus 1, x of n minus k. That means this k is varying from 0 to m minus 1. For example, if m equal to 3, then the equation becomes y of n equal to 1 by 3. This becomes 1 by 3, and this is 0, that is x of n for k equal to 0, and 1, it is x of n minus 1 plus x of n minus 2. It takes 3 samples, the present sample, the previous one, and the x of n minus 2. So 3 samples, add it and average, getting the average. So this as a signal comes in, so the 3 samples of it is taken and averaged, and then the window is slided, and then take another 3 samples and average it, and then another 3 samples and average it, and so on. So this would be useful. This particular system, discrete time system, is useful for averaging the signal. This is for m equal to 3. Similarly, for m equal to 5, that would go up to n minus 4 here. Okay, so this would take n minus 1, n minus 2, n minus 3, n minus 4, and average it by, that is for up to the 5. So 5 samples will be taken and average it. So similarly, this can be of any window length. And the accumulator, so you want to accumulate the value, which is the signal values which is coming in for certain time, and then do the processing. Okay, so this is going to be the accumulator y of n, where k is varying from minus infinity to n. There are 2 representation to have this accumulator x of k. So where minus infinity, the time, suppose is minus infinity in the sense minus 5, for example, minus infinity to present instant n. So how do we write this? Minus infinity to that is n minus 1 till that point, what is the x of k, and the nth instant can be separately added plus x of n. So this would take care of the past values, and this is taking care of x of n, the present input. So the past values can be, the summation would be represented as y of n minus 1. So y of n equal to y of n minus 1, the past value is the sum of the accumulated x of n up to n minus 1th instant, that is termed as y of n minus 1, and this is the present instant input. So this is also an accumulator system. X of n is added with the past input values, and then the same accumulator can be represented in other way as well. So instead of having it from minus infinity to n minus 1, okay, so this is minus infinity to minus 1, take it all input x of k, and then from 0 to n we take it as in a separate summation. So in that way, this can be a constant value, minus infinity to minus 1, this is constant. From k 0 to n we can represent it in the summation. So this is going to be y of minus 1 as an initial condition. So y of minus 1, this y of n has some value y of minus 1, and k equal to 0 to n is the summation. This would start adding the inputs from 0 to n, and the previous values are considered to be initial value. So there are 2 ways to represent this accumulator, n greater than or equal to 0, this is valid here. And we take the median filter. So always we apply this median filter in the images or the 2-dimensional signals also. Or this is shown for an 1D signal, where y of n is equal to median of x of n minus k, x of n minus 1, this goes up to x of n is here, x of n plus 1, and then it goes up to x of n plus 3, n plus k. So if suppose we take the median filter window of 3, So, x of n minus 1 and x of n plus 1, these 3 values are taken. Okay, so and then slide it, and you can keep find the median value, and then slide it once and take another 3 values, and what is the median of it, and it continues. So, here the median, how do we compute? So, we arrange it for the given signal sample values, we arrange it in the ascending order, and then find the middle value, that is this x of n. If you have the multiple values, and you take the sum of the two center values, and take the average of it. So, that is the median. So, we compute the median in the way, put it in the ascending order and take the median value. So, when we do it as for a signal which is coming in, actually the moving signal, then we need to have the window for a median filter. So, either it can be a 3-point median or a 5-point median. It can be of a length, different length. We would see that how this median filter is used in the case of filtering in the image or 1D signals. That window should be fixed, that is n minus k to n plus k. So, for finding the median of each window would result in a y of n, that is the response of the median filter. And upsampler, which is also used in the signal processing, when the signal sample rate increasing the sample rate, this upsampler is used, in which the y of n equal to x of n by l and 0 otherwise. This is valid for n equal to 0, plus or minus l, and plus or minus 2l. So, for example, here this x of n has signal which is having x of 0, x of 1, x of 2 and x of 3 and so on, x of minus 1, x of minus 2 and so on. So, x of this is n by, suppose l is 2. Okay. So, then the upsampler between 0 and 1, there are l minus 1 zeros are introduced. So, x of 0 will be there, and there will be 1 0 introduced, and x of 1, then 1 0 will be introduced, x of 2 and 0, x of 3 and so on. So, that is n minus 1 or the number of upsampling, that is going to be, suppose it is 2, that is 2 minus 1, 1 0 in between will be introduced in the samples, that is y of n, that is upsampling. Here similarly minus 1, x of minus 1, you will have 1 0 in between in the sequence what we have for x of n, and this is 0 for other cases. Okay, so in this also we need to note down that n is 0. If we put n equal to 0, so that is this x of 0 is can obtain. If n equal to 1, that is 1 by 2, that signal is not existing here. So, that 1 by 2 does not have, that is the meaning of 0 otherwise, and it is 2, if it is 2, 2 by 2, that is the signal x of 1, and if it is 3, 3 by 2, 1.5, that signal is not available, that is 0 otherwise. That is, if it is 4, and that is going to be x of 2 and so on, that would have this in between values are one values would be 0. So, whereas this is upsampling, and the case of downsampling, so you have sampled the signal for too much sampling rate. So, you want to downsample the signal. So, then that is possible, the system which is used for this y of n equal to x of mn. M is the integer, where m can be suppose for example to 2 times I want to reduce the sampling rate. In that case, x of this is going to be 2n. Okay. So, for this x of n, well, if x of 2n is to be applied, so then it would collect x of 0 and this n equal to 0, and n equal to 1 would go and pick up this 2. So, x of 2 would be the y of n, the next sample, and x of this one would pick up the x of 4 and so on. So, this is y of n now. Okay, I am just giving from n greater than 0, and similarly this is valid for n less than 0 as well, 0, 2, 4, 6, 8 and so on. So, those samples are picked up. So, this 1, 3 are neglected in that case. So, in downsampling you will lose the information. So, when we downsample it. So, these are few examples, and there is another some forward difference equation which y of n equal to x of n plus 1, see there is a future sample minus x of n. So, the difference between that is y of n. This is one forward difference system. Also, the backward difference system, y of n is x of n minus x of n minus 1. So, this is also a system used generally, forward and backward difference systems. So, these are some of the examples I have given for the discrete system. So, we have seen the classification of signals, the time operations, especially combining the signal operations, what shifting and scaling, how do we combine that, what is the precedence rule for it, shifting and then scaling, or if you want to do the scaling and then shifting, then in the shifting process we should take care of the scaling parameter as well. Now the thing of systems are introduced. What is the definition of the system? How can we classify the system? A few system classification has been dealt, that is linear and non-linear systems, causal and non-causal systems, memoryless and memory systems, and time invariance system. So those been given. So the remaining part of the systems, like the remaining classifications, we'll do in the next lecture. Thank you.